across the surface of our planet. More than 200 massive impact craters have been recorded as the scars left by celestial bodies that once tore through the atmosphere and slammed directly into Earth. The most prominent among them is the Chicxulub crater on the Yucatan Peninsula, the site of an event that altered the global climate and wiped out 75% of all life, marking the catastrophic extinction of the dinosaurs around 66 million years ago. Scientists estimate that millions of near-Earth objects, or NEOs, asteroids, and meteoroids remain hidden in space, and one of them could pose a direct threat to life on Earth. What would happen if an asteroid suddenly came hurtling toward Earth? With the advancement of technology, humanity is striving to find ways to prevent such a catastrophe. From early warning systems to asteroid deflection missions like NASA's DART, do we truly have enough time and the necessary technology to stop one, or even multiple, planet-killing threats? Let us explore the mysteries and challenges we face. About 4.6 billion years ago, as the sun was forming from a vast cloud of gas and dust, leftover material that failed to coalesce into full-fledged planets became asteroids. These objects carry fossilized memories of an era when physical laws were still chaotic, when orbits had not yet settled, and collisions were frequent and violent. Today, most asteroids are concentrated in the main asteroid belt, located between the orbits of Mars and Jupiter, at an average distance of about 2.1 to 3.3 astronomical units from the Sunday. Within this belt, Jupiter's immense gravity, combined with gravitational resonances, constantly stirs the region, occasionally nudging an asteroid out of its stable path and onto an orbit that crosses Earth's. From that moment on, it becomes a near-Earth object, or NEO. A well-known example is Apophis, an asteroid roughly 370 meters in diameter, discovered in 2004. Early orbital models suggested a collision probability with Earth in 2029 high enough to alarm the global scientific community. Although later, more precise measurements ruled out that risk, Apophis remains a stark reminder. These ancient fragments never disappear. They remain silent until their paths intersect with ours. Based on chemical composition, scientists classify asteroids into three main groups. C-type asteroids make up about 75% of the population and are rich in carbon compounds, water, and primitive organic molecules, true time capsules of prebiotic chemistry. Silicate asteroids contain abundant rocky minerals and metals and are more common in the inner regions of the belt. Finally, M-type asteroids are rich in iron and nickel, remnants of shattered protoplanets, with densities high enough to penetrate Earth's atmosphere and cause severe damage upon impact. What ultimately determines an asteroid's destructive power is its size and speed. An object only a few dozen meters across, striking Earth at a typical velocity of 20 to 25 kilometers per second, can release energy equivalent to tens of megatons of trinitrotoluene, or TNT. In the cosmos, mass combined with velocity does not merely create motion, it creates catastrophe. So how many of these objects truly pose a threat to Earth today? Modern science has shown that Earth is constantly moving through a steady rain of material from space, tracked, measured, and modeled on a daily basis. According to NASA estimates, roughly 40,000 to 100,000 tons of cosmic dust and small meteoritic fragments enter Earth's atmosphere every year. Most of this material ranges in size from grains of sand to a few centimeters across, burning up high in the atmosphere and vanishing as harmless streaks of light we recognize as meteors. Yet, even an asteroid just 20 to 50 meters in diameter is enough to produce an airburst with energy comparable to a nuclear weapon. The Chelyabinsk event in 2013, caused by an object approximately 19 to 20 meters wide, released an estimated 400 to 500 kilotons of TNT, shattering windows in more than 7,000 buildings and injuring over 1,500 people. The most troubling aspect was not the power of the explosion itself, but the fact that the object went completely undetected before it entered the atmosphere. On larger scales, geological history preserves unmistakable scars, such as the Barringer crater in Arizona, also known as Meteor Crater, formed by an iron-nickel asteroid only about 40 to 50 meters across, yet releasing energy equivalent to roughly 10 to 20 megatons of TNT. To date, observation programs have identified more than 32,000 near-Earth objects, of which about 10,000 to 11,000 exceed 140 meters in size, a threshold large enough to cause regional or even national-scale devastation. The greatest concern, however, lies with mid-sized asteroids, roughly 100 to 300 meters across. These objects are large enough to destroy a megacity, ignite widespread wildfires, and trigger short-term climate effects, yet they are significantly harder to detect than larger bodies. A recent example is 2024 YR4, an object flagged for close monitoring because its estimated size would be sufficient to cause catastrophic urban destruction in the event of a direct impact. Many of these objects are detected only days, sometimes mere hours, before they pass close to Earth. Optical telescopes struggle to detect small, dark objects with unusual orbits. Particularly dangerous are asteroids approaching from the direction of the Sun, a region scientists refer to as an observational blind spot. Statistical models suggest that tens of thousands of objects larger than 50 to 100 meters remain undiscovered. And once the numbers are tallied, the size is classified, and the orbits calculated, what would actually happen if one of the largest, rarest, and most dangerous of these objects did not merely pass by, but struck Earth head-on? An asteroid roughly 10 to 15 kilometers in diameter, comparable to the object that created the Chicxulub impact crater, would slam into Earth at an average speed of 20 to 30 kilometers per second. Speed alone would be enough to turn that massive rock into a weapon far beyond anything humanity has ever built. The energy released in a single instant is estimated to exceed the combined nuclear arsenal of the entire human civilization by millions of times. The first moment unfolds the instant the asteroid makes contact, as both the object itself and Earth's crust at the impact site are almost instantly vaporized. Pressure spikes to hundreds of gigapascals, while temperatures soar beyond 20,000 degrees Celsius, hotter than the surface of the Sunday. An impact crater 150 to 200 kilometers wide forms, followed immediately by shock waves racing outward at supersonic speed. Within thousands of kilometers, every structure from mountains to cities is crushed, not collapsed, but shredded by a sudden and overwhelming surge in atmospheric pressure. But the destruction does not stop at the surface, as vast quantities of material are blasted into the atmosphere and even beyond near-Earth space. Glowing hot fragments rain back down over the planet for hours, creating a global thermal storm. The heat released is sufficient to ignite continental-scale wildfires, even in regions located half a world away from the impact site. No lava is required, no volcanoes are needed. The sky itself becomes the source of fire. The impact also drives immense energy deep into Earth's mantle, triggering worldwide earthquakes as geological faults activate simultaneously. If the collision occurs in an ocean basin, tsunamis hundreds of meters high form near the impact zone, racing across the oceans at jetliner speeds and striking coastlines for hours or even days after the initial event. Hundreds of billions of tons of fine dust, pulverized rock, and sulfur compounds from heated sedimentary layers are injected into the stratosphere. Climate models show that sunlight would be blocked on a global scale, causing average surface temperatures to plunge by 10 to 20 degrees Celsius in a short time. Photosynthesis nearly grinds to a halt, and the surface layers of the oceans cool rapidly, shattering biological equilibrium. On land, growing seasons vanish. Earth does not explode, but every system that sustains life is broken at every level. At this stage, complex life is not wiped out by the impact itself, but by the long years that follow when skies remain dark, temperatures collapse, and solar energy can no longer reach the surface. If a single planet-killing impact is enough to push Earth into total systemic collapse, what happens if the scenario is no longer a single strike? What if multiple asteroids impact together, or a chain of collisions unfolds over a short span of time? In the early history of the solar system, events such as the Late Heavy Bombardment around 3.9 billion years ago show that young planets once endured waves of impacts within the same geological period. Earth survived, but with a biosphere utterly unlike the one we know today. The question is whether modern Earth could withstand anything similar. In this scenario, geophysical models suggest that the planet's upper crust would be extensively restructured. Thousands of impact sites would generate localized melt zones, weakening tectonic integrity. Tectonic plates would not merely shift, they could destabilize on a global scale, triggering chains of volcanic activity lasting for years. This would not be a single supervolcano, but hundreds of magma systems activated simultaneously. The oceans covering most of the planet's surface would become a central driver of the catastrophe. Each ocean impact would inject enormous energy directly into vast water masses, locally heating the upper layers of the seas. With enough impacts, portions of the oceans could temporarily vaporize, pumping immense amounts of water vapor into the atmosphere and disrupting global thermal balance and atmospheric circulation. The atmosphere would then absorb a double shock from below: water vapor, ash, and sulfur gases released by impacts and volcanic eruptions. From above, incoming solar radiation would be sharply reduced by a dense veil of fine dust in the stratosphere. The result would be severe thermal imbalance, surface temperatures dropping rapidly, while upper atmospheric layers heat abnormally. Climate models indicate that this upheaval could persist for decades, even centuries, before Earth slowly regains any relative stability. In such an environment, complex life would be nearly impossible to sustain. not because every organism is instantly annihilated, but because the systems that support life collapse simultaneously. Food chains lose their foundation. Plants can no longer maintain stable photosynthesis. Herbivores disappear, and predators soon follow. A single impact allows a planet to enter a recovery phase, however slow. But when impacts arrive in rapid succession, there is no biological pause. Life has no time to adapt, migrate, or evolve. Conventional survival strategies, hibernation, movement, biodiversity, become meaningless when environmental change outpaces genetic response. This scenario reveals that planetary stability exists only under very specific conditions. When disruptive events accumulate densely enough, that balance can be erased entirely, pushing Earth back toward a near prebiotic state. And just one sustained chain of impacts could plunge the planet into a prolonged cold and dark era, what science calls an asteroid winter. Everything begins with fine dust micrometer-sized mineral particles launched into the stratosphere at altitudes of 15 to 50 kilometers, where rain cannot wash them out. The immediate consequence is a sharp reduction in the amount of sunlight reaching Earth's surface. Global climate simulations show that this reduction can exceed 60 to 80% in the first months. Earth no longer receives enough energy to maintain thermal equilibrium. The planet's surface cools rapidly. Within just a few months, average global temperatures can drop by 10 to 15 degrees Celsius, with far greater declines at higher latitudes. The loss of sunlight triggers a global disruption of photosynthesis. At the same time, the atmosphere enters a prolonged state of instability. Fine dust and sulfur aerosols reflect incoming sunlight while trapping heat in the upper layers, creating an abnormal temperature inversion. This imbalance breaks down atmospheric circulation, causing monsoon systems to disappear and rainfall to become rare and unpredictable. Many regions fall into prolonged drought, while others experience acid rain as sulfur combines with atmospheric water vapor, making Earth increasingly hostile in every physical sense. According to post-Chicxulub climate models, this abnormal cold state can last 10 to 20 years before sunlight gradually returns to levels sufficient for photosynthesis to recover. By then, soils are depleted, ecosystems are fractured, and biodiversity has been severely reduced. An asteroid winter does not end when the dust settles. It leaves behind a post-crisis era that can persist for centuries. The dust does not come from burning cities, but from rock and sediment pulverized on a planetary scale. This is the moment when Earth reveals itself as a system utterly dependent on the flow of solar energy. When that flow is cut off for long enough, evolutionary achievements built over hundreds of millions of years can collapse within a single generation. If this chain of effects can last for decades long enough to erase most complex life, does life vanish entirely, or does it merely retreat, waiting for a chance to return? Extinction does not mean the end of life, and across Earth's 5 major mass extinctions, including the event 66 million years ago, there were moments when more than 75% of all species vanished. And yet, life was never completely erased, because life on Earth is built in multiple biological layers, each with very different levels of resilience. The most persistent survivors are always microorganisms. Bacteria, archaea, and single-celled organisms can endure conditions that seem impossible. Temperatures above 100 degrees Celsius, pressures hundreds of times greater than atmospheric levels, extreme pH values, and even environments with almost no light. Research on extremophiles shows that many microorganisms can enter prolonged states of biological dormancy lasting thousands, even millions of years, waiting for favorable conditions to return. At depths of several thousand meters, where temperatures remain stable, ecosystems based on chemosynthesis can continue to exist. Hydrothermal vents on the ocean floor, where organisms draw energy from chemical reactions involving sulfur and metals, are almost entirely independent of the sky above. Similarly, deep within soils and active rock layers, many microbial species have been found living more than 2-3 kilometers beneath the surface, where temperatures and pressures are high but stable. There, life proceeds slowly, consuming energy at minimal rates, largely isolated from surface-level catastrophes. By contrast, large animals, higher plants, and complex ecosystems suffer the greatest losses. They depend on continuous energy input, stable cycles, and relatively predictable environments. When those conditions vanish for years or decades, complex life simply has no time to adapt. Earth's history reveals a striking pattern. After catastrophe, evolution often accelerates. When biodiversity collapses, countless ecological niches are left vacant. The survivors, typically small, simple, and flexible organisms, rapidly adapt and diversify. After the Chicxulub impact, within just a few million years, mammals rose from small, shadow-dwelling creatures to become the dominant life forms on land. Catastrophe does not create new life, but it redistributes evolutionary opportunity. If life itself will continue, then the question becomes unavoidable. What, if anything, can humanity do in the face of a threat arriving from the cosmos? Over the past few decades, humanity has built a global space monitoring system, including ground-based telescopes and dedicated satellites, such as large-scale sky surveys that allow the detection and tracking of tens of thousands of near-Earth objects. Modern orbital science makes it possible to predict the trajectories of hazardous objects with high accuracy for many years, even decades, if observational data is obtained early enough. The next step is active defense, commonly known as planetary defense. Rather than destroying an asteroid, current scientific strategy focuses on altering its orbit. Changing an object's velocity by just a few millimeters per second, if done early enough, can cause it to miss Earth by thousands of kilometers years later. Controlled impact missions have demonstrated that humans can produce measurable effects on the orbit of a celestial body. Alongside this are multi-layered response scenarios in which, if a threat is detected decades in advance, orbital deflection is prioritized. Dealing with a massive asteroid on short notice, involving objects several kilometers in size and warning times, measured only in years or months, renders all current options impractical. The energy required to deflect or disrupt such a celestial body far exceeds humanity's ability to deploy it rapidly. Another major limitation lies in observational blind spots, as objects approaching from near the direction of the sun or with extremely dark surfaces remain a serious challenge. Even as observation systems continue to expand, there are still regions of space we cannot observe early enough. This means that some dangerous scenarios may only be detected when the remaining response time is already too short. In such cases, planetary defense effectively shifts from prevention to damage mitigation. Finally, there is the inability to fully control the post-impact environment. Even if humanity fails to prevent a collision, response plans can still be prepared. However, geological history shows that climate systems, ecosystems, and geochemical processes can react in non-linear and highly unpredictable ways. No existing technology can fine-tune the global climate, after a planet-scale shock. Humanity now stands in a transitional phase of civilization, advanced enough to recognize cosmic threats, humble enough to acknowledge its limits, yet still learning how to act collectively in situations far beyond historical experience. Does our survival depend more on technology itself, or on how we choose to use it? Planetary defense is not merely a problem of physics, but a question of priorities, cooperation, and long-term vision. What do we learn about ourselves by confronting such extreme scenarios? The first lesson, and also the hardest to accept, is that Earth is not immutable. Geological records show that climate, oceans, the biosphere, and even the planet's crust have undergone violent changes many times throughout history. From this follows the fragility of life, diverse ecosystems, long food chains, and the civilizations built upon them. A sufficiently large shock, or a prolonged sequence of disruptions, can cause these structures to collapse far faster than the time it took to build them. This reminds us that evolution is not a straight upward path, but a process that can always be broken. And technology is not an absolute shield. Modern science gives humanity unprecedented power to predict and intervene, but it does not erase the laws of physics. The true value of technology lies in reducing risk, extending reaction time, and opening up more options. From here, a social lesson emerges. Global cooperation is more important than competition. Extreme scenarios clearly show that no single nation can face a planet-scale disaster on its own. Asteroids do not choose impact sites based on borders, and their consequences do not stop at any territory. Another lesson, less emphasized but critically important, is scientific humility. Extreme scenarios force humanity to acknowledge that our understanding of the Earth system remains limited. Climate, ecosystems, and geophysical processes can respond in non-linear ways that go beyond intuition. We are in a transitional phase of civilization. Investing in planetary defense, fundamental science, or international cooperation may not bring immediate benefits, but it shapes the survival prospects of future generations. The history of the universe and the geological record both lead to an unavoidable truth. Earth exists within a constantly moving cosmos, where collisions, disturbances, and randomness are the rule, rather than the exception. Life on this planet has never been guaranteed. It has only ever been temporarily balanced under rare and favorable conditions. Every celestial object detected early is not merely a point of light in the sky. It is time-gained time to act, to cooperate, to choose the path with the least risk. In extreme scenarios, time itself becomes the boundary between control and helplessness. Humanity cannot control the universe, and perhaps never will. The story of asteroids is not told to spread fear. It exists as a clear-eyed reminder. Life on Earth is more fragile than we often assume, but its future, at least in part, still rests in the decisions humanity makes today. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.